we're going to be taking a look at the antiderivative of absolute value functions. For this first example, we're just going to do integral or antiderivative of absolute value of x. So how can we figure out an antiderivative of an absolute value function? That's going to be the gist of this lesson. Well, first of all, it's important to note that the absolute value function is basically taking the original. So let's just say we had y equals x, which is just a diagonal line going through the origin. The absolute value of x is basically taking this line, this part of the line that's below the x-axis, and flipping it up to make this V shape. So this is what the absolute value of x would look like. So, the question is, how can we use that information to find the antiderivative of the absolute value of x? I want to go through some steps with you to figure out the antiderivative of any absolute value function. Right now, like I said, it's just absolute value of x. For the next example, it'll be a little bit more involved than that. So the first thing you're going to do is to determine x-intercepts. Now, why are we determining x-intercepts? Because only at an x-intercept can the graph go from negative to positive. And the real concept of an absolute value is to take anything that's negative, flip it, make it positive. What are the x-intercepts of y equals x? So what we're doing is we're just focusing on what's in the absolute value bars, which is just the x. So anyway, that x-intercept would be 0. That's all you're going to do for step 1. Okay, you're just going to determine what the x-intercepts are. In this case, we can see it crosses at x equals 0. All right, step 2, we're going to come up with a sign chart. Now, what is a sign chart? It just tells you whether the function is positive or negative on any given interval. So let's read kind of what I've got written right here. What's that? A special note, you are plugging in the test value into the function without the absolute value. So what I'm talking about is when you do your sign chart, you're just plugging it into, in this case, x, not the absolute value bars. And that's because we're kind of looking at the parent function, not without the absolute value bar. So we're talking about this function right here, where it's just x, not absolute value of x. So let's take a look. We only have 2 intervals, and that's based on our x-intercept of x equals 0. The first interval is going to be from negative infinity to 0. And then the second interval is from 0 to infinity, and again, that's just based on that one x-intercept we had. So plug in negative 1 into y equals x, we get negative 1 back, right? What that tells us is that this function is going to be negative from negative infinity to 0. Now this one's really easy because we've already looked at the graph, and y equals x is pretty much the simplest function possible, but these steps are going to help you when we look at the next example, which is more complex. Since we get a negative back, we know that this function is going to be negative on that interval from negative infinity to 0. Same way, from 0 to infinity, when we plug in 1, we get 1 back. We're going to get positive back, so it's going to be positive on the interval. This leads us to step 3, which is our ultimate goal here. We want to break down the absolute value function into a piecewise function. What does that mean? It means to multiply the pieces of the function that are negative by negative 1. Keep the positive pieces positive. All right, so that's a lot of words. Let me explain what that means. So we basically said that on the interval from negative infinity to 0, this function is negative. Now, why are we multiplying it by negative 1 for step 3? Well, anytime you have a piece of a function that's below the x-axis, if you multiply it by negative 1, if you remember from function transformations, you're flipping that piece of the graph up. In the case of y equals x, if you take this piece, and I'm going to use some color here, this piece, and you multiply it by negative 1, it will in effect flip it. It will take that part of the graph, flip it up like that. And that's true for any function, not just y equals x. So basically, we're taking this graph right here, and we're converting it to an absolute value function, but we're going to do it as a piecewise function. So we can see this piece of the graph is going to be y equals negative x, and that's what happens when we multiply this by -1, right? So it goes from y equals x to y equals negative x for this piece. Now the piece that was already positive, we're keeping the same. We don't have to multiply that by -1 because it's already above the x-axis. So that leads us to this piecewise function, meaning that the absolute value of x can be rewritten as negative x for x is less than 0, and positive x for x is greater than or equal to 0. And if you graph it again, you'll get this v, which is the same as the absolute value of x. Now you might be saying, okay, why do we convert it to piecewise? Well, we're trying to find the antiderivative. When you have these two separate pieces, you can take the antiderivative of each piece easily. For example, the antiderivative of x is the same as, this is x to the first. It's going to be x squared over 2, right? You can do the same thing for this. So it just makes it antidifferentiable. You break it into a piecewise function, for example 3, for that reason. That way we can find its antiderivative. So that leads us to step 4. Simplify the piecewise function. Now this one's pretty simple. I mean, if negative x just becomes negative x, positive x just becomes x. And so again, this step is going to be more obvious for the next example when it's more complicated. But for now, I just know that you need to simplify that. And then now we can antidifferentiate. Now, what we're really doing for step 5 is we're antidifferentiating each piece. So one piece at a time. That. So basically what I do is I just put my antiderivative sign for each piece, antiderivative of negative x, antiderivative of x. Again, the top piece is for x is less than 0, bottom is for x is greater than or equal to 0. The antiderivative of negative x would be the same as antiderivative of negative x to the first, which would be negative x squared over 2, or negative 1/2 x squared. Bottom piece would be positive 1/2 x squared. Again, that's the reverse of the power rule. Now up here I have a plus c because I took the antiderivative, meaning that constant could be anything. On the bottom, I just put plus k as a different constant, even though plus c would technically work. And that's actually it. That is going to be our antiderivative of absolute value of x. We have two pieces, negative 1/2 x squared plus c for x is less than 0, and positive 1/2 x squared plus k for x is greater than or equal to 0. And so you get a piecewise function as your antiderivative, just because it's really hard to take the antiderivative of this without breaking it up into separate pieces. It's going to be even more difficult as we look at the next example, which is even more complex. I do want to show you kind of what this graph would look like if you were to graph it. Negative x squared, or negative 1/2 x squared for x is less than 0, is going to kind of look like this actually. All right, and then positive 1/2 x squared for x is greater than or equal to 0 is going to look like this. So it kind of looks like an x cubed function. Again, the reason this is the antiderivative is because if you take the derivative of this, you will actually get absolute value of x back. And again, the derivative is just the slope of the tangent lines. And you can see the slope of this one. At any given x value, it's just going to be negative x. For example, at x equals -2, the slope of the tangent line would be positive 2, because it'd be negative, right? You can kind of see it would be positive 2. And over here, slope of the tangent line at, say, 2 would also be the same slope on this purple line. Would also be 2. So the antiderivative of absolute value function is a piecewise function that kind of looks like x cubed. That's it for this example. If you have any other questions about it, let me know.